Good morning, ladies and gentlemen. Welcome to our video on Bernoulli distribution and the binomial probability distribution. It's going to be quite a long one, so get comfy, get caffeinated, ready to take plenty of notes. Alright, Bernoulli distribution occurs when there is a single event happening. So a single toss of a coin, a single roll of a dice, where there can only be two outcomes. So a single toss of a coin, obviously head, tails. Single roll of a dice might represent even number, odd number, or a 6 or not a 6. So where there are two outcomes, one which represents a success and one which represents a failure. And the Bernoulli distribution always looks like this. The success will have a value of 1 and the failure will have a value of 0, or the not success will have a value of 0. And the probability of success is always denoted by P, and therefore the probability of not a success is 1 take P. And this leads us to a few simplifications in the expectation and variance formula. So expectation is there is a 1 take P chance of a failure, or not a success, so it's 0, and that means the expected value is simply P. And similarly, following through a substitution with the variance formula, the variance is P bracket 1 take P for this distribution. And note the standard deviation will be the square root of that. So standard deviation is as above, but the square root of. Now, Bernoulli doesn't come up very often, simply because it only is one occurrence. But we'll go through one example from the book. If let x equal 1 if there is rain tomorrow. So rain tomorrow here is what we would call a success. X equals 0 if there is no rain tomorrow. The probability of rain, P, equals 0.4. So probability distribution for x, it's either going to be 0 at the top or 1. And the probability distribution for x, these are the x. This is the probability that something equals x. And the distribution here is 0.4, and this would be 0.6. Right. What is the mode of the distribution? Well, the mode is the most commonly occurring, 0.6. The 0.6 chance it will not rain. The expected value here, because it's Bernoulli, we don't have to do the maths. The expectation is just going to be 0.4, so that is 0.4. The variance will be P times 1 take P, so that is 0.4 times 0.6, it's 0.24 is the variance, and then the square root of that would be the standard deviation. Alright, now moving on very quickly to something that comes up much more often. It's called a binomial experiment, and this is essentially a Bernoulli that happens many times. So similarly, there's a success or a failure, or a success and not a success, but it's like rolling a dice 10 times, 20 times. And any trial of the experiments, any particular roll or any particular shot with a dart or success, failure, there is a probability of success is P, sorry I partially covered that there, and the probability of failure is 1 take P. Now note, in this repeated experiment, each trial is independent, and that's very important. It's not a binomial experiment unless each trial is independent. Independent means each trial does not affect the successive probability. So for example, if you roll a dice, each roll of the dice does not affect what happens next. So if I roll a 3 and a 3 and a 3, by probability of rolling a 3 the next time isn't changed. For another example of an independent probability would be tossing a coin. There are plenty of people who think they've tossed 4 heads in a row, therefore they're more likely to get a tail the next time. Those people are idiots. It makes no difference, they're independent each time. An example of a binomial type experiment that wouldn't be independent might be tennis sets. Say you're playing sets of tennis against someone, and your confidence increases if you win and decreases if you lose. The probability of you winning and losing each successive set changes. So if the probability of losing changes based on what happened previously, then it's not independent, and therefore we would not apply any of this maths to it. So the maths that follows only applies if it's independent trials. Alright, so binomial variable x is the total number of successes in n trials. Alright, now there's a very confusing formula to do with this, and I'll try and describe where the formula comes from by looking at the probability, well, of tossing an unfair coin, what the outcomes are when the probability of tossing a head, so the probability of a head here is 0.75. Now if we're looking at the coins, we have our first toss, which is either going to be a head or not a head. excuse my writing, second toss, I've left myself not a lot of space, is head, not a head. Third toss, head, not a head, head. Why do I keep doing that? Not a head. No, the dash means not, if you haven't got there already. Head, not a head, head, not a head. Alright, now here we would like to look at some probabilities. So without me writing in each of the probabilities that each of these branches are going to be the same. It's going to be 3 on 4 here, or 0.75, and 1 on 4 there, and so on the whole way through. Alright, that's the vacuum cleaner, so I may have to pause this as the cleaner comes through. Alright, but anyway, to get 3 heads, this outcome here is going to be 3 on 4 to the power of 3, because we've multiplied along there. To get this outcome here of 2 heads and not a head, we'll have 3 on 4 to the power of 2 multiplied by 1 on 4. And I'll continue going down, and I'll pause it while I can continue going. Alright, so all the probabilities have been written out in my terrible writing. And the way each of these are calculated is every time we go along a head path, we have a 3/4 chance following that, and a not head is a quarter. So 3/4, 3/4, not is that. Here it's 3/4, quarter, 3/4. So I've just done the 3/4 squared. Now I'd like to examine the probability of each different type of outcome. So the probability of getting 3 heads is 3 on 4 to the power of 3. And similarly easy to follow is the probability of getting 3 tails is 1 on 4 to the power of 3. Now the two outcomes in the middle, we're assuming here that order is not important. So if an examiner asks you what's the probability of getting 2 heads then a tail, you must follow this path here, because that represents 2 heads then a tail, or 2 tails then a head. However, if the question asks what's the probability of getting 2 heads and a tail, then order is not important. And 2 heads and a tail can look like this. 2 heads and a tail, head, tail, head, tail, head, head. So really here there are 3 ways of doing this, and each of them, if you notice the blue lines, has 3 on 4 squared, then 1 on 4. And here we can look at probably 2 tails and a head. So 2 tails and a head would be there, there, and there. And there's 3 lots of this, so we'd add them all together. 3 on 4 to the 1, 1 on 4 squared. Now I've made rather a mess of that, but there's quite a neat pattern here in what's happening. Firstly, note how each time the powers change. So for the power here of 3/4 is going from 3 to 2 to 1, and then there's no power of 3/4 there, it's not there. And the other power is increasing. So the power of quarter starts at 0, then it goes to the power of 1, 2, 3. And this is what's known as a binomial expansion pattern. Similarly, the coefficients are 1, 3, 3, 1. And I'm hoping you've seen binomial expansion in the past. But it can be applied to probability distributions like this. So, this here is a formula for binomial expansion. And it looks very scary, but let me talk you through it. Say we want to expand something out like this. A plus B to the power of n. Well, the way we expand this is the sum of all n choose k, a to the k, b to the n take k. Where this here is shorthand for n choose r or n choose k. Sorry for the mix up. That everywhere you read that should be k, and so should that, and so should that. to make it work. In the apologies, I didn't realize that R was K. Okay, here. In the textbook, it talks in terms of K. In your calculator, it talks in terms of R. Let's just do an expansion, and you'll see how this formula works. So, if we're to expand this out, we first of all start with n, so C, 5, choose 0. Oh, not good. 5, choose 0. 9 on 10 to the 5. 1 on 10 to the 0. Plus 5, choose 1. So 5, choose 1. 9 on 10 to the 4. 1 on 10 to the 1. And then this pattern keeps going. Let me just explain, well, before I continue it, I'll explain a few things that are happening. Firstly, this 5CO, 5C1 is a formula that can be written like that with factorials, but you don't particularly need to know that. What would be more useful for you to know is how to get to it in your calculator. So here, you go into ordinary run mode, you go options, across, probability, and then there's this one here. 5C0 should come up as 1. And then 5 choose 1 should come up as 5. I'll check that in a sec. 5 choose 1 up as 5. 5 choose 2 should come up as 10. Now you might ask me, how am I predicting them? Well, the prediction is related to Pascal's triangle. That's this triangle here. You'll have seen the pattern before. The cool thing is, each of these rows has a number. So think about this as 1, 2, 3, 4, 5 row. So 0, 1, 2, 3, 4, 5. And then these numbers make up the coefficients. 1, 5, 10, 10, 5, 1. And a way of calculating them quickly is using this NCR or NCK model. So 5 choose 3 is 5th row, 3rd number in. So 5th row there is 5 choose 3. I know that's the 4th number in, but that's choose 0, choose 1, choose 2, choose 3, choose 4, choose 5. This C thing lets us locate things quickly in Pascal's triangle. And note, up above, how we were looking at 1, 3, 3, 1. That could easily be written as 3 choose 1. And this here was 3 choose 0, and that there was 3 choose 2, and this here was 3 choose 3. If you plug those into your calculators, you'll get those numbers out. Those numbers out relate to the 3rd row of the Pascal's triangle. Alright, so continuing this expansion. You can pause and get a coffee any second, anytime you want. Continuing this expansion, I'm not going to bother writing 5C1, 5C2, etc. Instead, I'll simply write the coefficients. So really, that there is 5, and this here is 1. Plus, and then 10, or 5 choose 2. Lots of, apologies, 9 on 10 to the 4, multiplied by, not 4, we did 4 last time, 3, 1 on 10 to the 2, plus 10 lots of 9 on 10 to the 2, 1 on 10 to the 3. Keep going. Plus 5 lots of 9 on 10 to the 1, 1 on 10 to the 4, plus one lot of, well, 9 on 10 to the 0, 1 on 10 to the 4. And note, 9 on 10 to the 0 is just 1, so we can almost ignore it. That just goes out to 1. In the same way, over at this end, 1 on 10 to the 0 is almost 1. Now, that there would be painful to put in your calculator, but you could. Alright. How could that possibly relate to probability? Well, here's how. So, this is the binomial probability distribution function, which is very much related to the binomial expansion before. So, here is the number of ways k successes can be ordered amongst n trials. So, up above, in the dice, the number of ways we could get 2 heads from 3 trials was 3, because that was 2 heads coming out in those 3 there. P is the probability of success to the power of k minus 1 take p to the power of n take k. And if something is binomially distributed, we say that x, that symbol there, is distributed binomially. N is the number of trials, and P is the probability of success as each trial occurs. Alright, so say an archer has a 90% chance of hitting a target with an arrow. If 5 arrows are fired, determine the probability or the chance of hitting twice only. Now this expansion here is the binomial expansion we did above. 1 on 10 to the power of 5, with a 9 on 10 to the power of 5 there. So they've just reversed it slightly. We started with 9 on 10, same thing though. Note here, 9 on 10 is the probability of a hit. So 9 on 10 to the power of 5 corresponds to 5 hits. And we could do this with the tree diagram and come up with the same effect. But obviously firing something 5 times is 5 sets of branches on the tree diagram, and it gets very tiring to draw. Even drawing 3 tosses of a coin was annoying. This here represents 4 hits. Note the 4 and the power of 4. So 4 hits. Probability of a hit is 9 out of 10. 4 hits is to the power of 4. 3 hits, power of 3, and same with the misses. So the probability of hitting twice only is this one here. And the probability of hitting at most 3 times is the probability of hitting all of those. So the probability of 0 hits, 1 hit, 2 hits, 3 hits, and adding them all up. Now that's quite a pest to do in your calculator by hand. But you could do it, and especially for low numbers of trials, say 3 trials, you'd expect to be able to write that out by hand and solve it by hand. Okay, however, using CAS. So let's solve these 2 problems again using CAS. In your calculator, you have to go into statistics mode and look at distributions and BN, BNN there. Now you have 2 options. BPD is a point distribution where you're looking for a specific result. So let's say we're looking for the result where he only hits the arrow twice. So there. Now note here, we want X is the number of successes, 2 hits. 5 is the number of trials, 5. P is the probability of a success. No, it has to be the probability of success, not the failure. So execute. And 1.8.1 e to the negative 3. E to the negative 3 means times 10 to the power of negative 3. So that 8.1 times 10 to the power of negative 3 is this solution here. Alright. Now, the probability of X being less than or equal to 3. Well, we could do it individually. The probability of 0 hits, 1 hit, 2 hits, 3 hits. Or there's this option here, distribution binomial BCD is cumulative, meaning this tests a range. So here we want the number of successes to be 3, and note that means up to and equal to 3. Execute 5 trials, P is none, and that there is 0.146, which is this answer here. Note when you go in here originally, This may look like a list. You don't want it as a list, you want it as a variable. Alright, now note, there's a trap here. That BCD function is called a tail left calculator. I'll explain what that means. So let's say the same archer, with the probability of hitting is 0.9, shoots 10 times. What is the probability that they hit less than 4 times? Alright, so once again, we're in BCD. Here, the probability of them hitting less than 4 times, we want up to or equal to 3. So we can leave that there as a 3, and we change that to a 10, and then we hit execute and calculate. And that's an incredibly small chance. So they're so good at hitting, the probability of hitting less than 4 times is really very small. What about 7 or more? The problem is, 7 or more, if you think about the number of times the archer can possibly hit, it's somewhere between 0 and 10. And what we're asking is, what's the probability of hitting 7 or more? Alright. Let's say, for the sake of argument, that probability is 0.8. We haven't calculated it yet, 0.8. We then know the probability of hitting less than is 0.2. Because we know that they are all the possible outcomes from 0 up to 10. The sum of the probabilities of the outcomes must equal 1. Our calculator can't calculate tail right. And this is incredibly, incredibly important. This is where people get tripped up in the exam. It cannot calculate this side directly. It only does tail left. So what you have to calculate is the left-hand tail and do 1 minus to get the probability on the right. So we need to calculate, in this case, the 0.2 in order to get to the 0.8. So for us to calculate the probability of hitting 7 or more times, what we're really going to say is we are going to do 1 minus the probability that x is less than or equal to 6. So the probability that he hits 6 or less times, and then do 1 minus that to find the probability of 7 or more. So in our calculator, we'll go up to 6, execute, execute. And that there is 0.1279, so the probability of hitting 7 or more times is 1 minus that value. Alright, I apologise that took so long, but there's a fair bit to get through. The important thing for you guys to know is this formula, how it relates to that ugly expansion, which I know brings in tree diagrams and Pascals, and it's kind of neat if you think about how it all fits together. And then how to answer these type of questions. Note that's an incredibly simple example. There will be another video with more complex examples if you'd like to look at it. Alright, thank you very much.